Class 12, Unit 5, Surface Chemistry. Objectives. After studying this unit, you will be able to describe interfacial phenomenon and its significance, define adsorption and classify it into physical and chemical adsorption, explain mechanism of adsorption, explain the factors controlling adsorption from gases and solutions on solids, explain adsorption results on the basis of Freundlich adsorption isotherms, appreciate the role of catalyst in industry, enumerate the nature of colloidal state, describe preparation, properties and purification of colloids, classify emulsions and describe their preparation and properties, describe the phenomenon of gel formation, list the uses of colloids. Some of the most important chemicals are produced industrially by means of reactions that occur on the surfaces of solid catalysts. Surface chemistry deals with phenomena that occur at the surfaces or interfaces. The interface or surface is represented by separating the bulk phases by a hyphen or a slash. For example, the interface between a solid and a gas may be represented by solid gas or solid/gas. Due to complete miscibility, there is no interface between the gases. The bulk phases that we come across in surface chemistry may be pure compounds or solutions. The interface is normally a few molecules thick, but its area depends on the size of the particles of bulk phases. Many important phenomena noticeable amongst these being corrosion, electrode processes, heterogeneous catalysis, dissolution and crystallization occur at interfaces. The subject of surface chemistry finds many applications in industry, analytical work, and daily life situations. To accomplish surface studies meticulously, it becomes imperative to have a really clean surface. Under very high vacuum of the order 10 raised to power minus 8 to 10 raised to power minus 9 Pascal, it is now possible to obtain ultra clean surface of the metals. Solid materials with such clean surfaces need to be sorted in vacuum, otherwise these will be covered by molecules of the major components of air, namely dioxygen and dinitrogen. In this unit, you will be studying some important features of surface chemistry such as adsorption, catalysis, and colloids, including emulsions and gels. Adsorption. There are several examples which reveal that the surface of a solid has the tendency to attract and retain the molecules of phase with which it comes into contact. These molecules remain only at the surface and do not go deeper into the bulk. The accumulation of molecular species at the surface rather than in the bulk of a solid or liquid is termed as adsorption. The molecular species or substance which concentrates or accumulates at the surface is termed adsorbate, and the material on the surface of which the adsorption takes place is called adsorbent. Adsorption is essentially a surface phenomenon. Solids, particularly in finely divided state, have large surface area and therefore charcoal, silica gel, alumina gel, clay, colloids, metals in finely divided state, etc. act as good adsorbents. Adsorption in action. First, if a gas like O2, H2, CO, Cl2, NH3 or SO2 is taken in a closed vessel containing powdered charcoal, it is observed that the pressure of the gas in the enclosed vessel decreases. The gas molecules concentrate at the surface of the charcoal, that is, gases are adsorbed at the surface. Second, in a solution of an organic dye, say methylene blue, when animal charcoal is added and the solution is well shaken, it is observed that the filtrate turns colorless. The molecules of the dye thus accumulate on the surface of charcoal, that is, are absorbed. Third, aqueous solution of a raw sugar, when passed over beds of animal charcoal, becomes colorless as the coloring substances are adsorbed by the charcoal. Fourth, the air becomes dry in the presence of a silica gel because the water molecules get adsorbed on the surface of the gel. It is clear from the above examples that solid surfaces can hold the gas or liquid molecules by virtue of adsorption. The process of removing an adsorbed substance from a surface on which it is adsorbed is called desorption. Distinction between adsorption and absorption. In adsorption, the substance is concentrated only at the surface and does not penetrate through the surface to the bulk of adsorbent, while in absorption, the substance is uniformly distributed throughout the bulk of the solid. For example, when a chalk stick is dipped in ink, the surface retains the color of the ink due to adsorption of colored molecules, while the solvent of the ink goes deeper into the stick due to absorption. On breaking the chalk stick, it is found to be white from inside. A distinction can be made between absorption and adsorption by taking an example of water vapor. Water vapors are absorbed by anhydrous calcium chloride but adsorbed by silica gel. In other words, in adsorption, the concentration of the adsorbate increases only at the surface of the adsorbent, while in absorption, the concentration is uniform throughout the bulk of the solid. Both adsorption and absorption can take place simultaneously also. The term sorption is used to describe both the processes. Mechanism of adsorption. Adsorption arises due to the fact that the surface particles of the adsorbent are not in the same environment as the particles inside the bulk. Inside the adsorbent, all the forces acting between the particles are mutually balanced, but on the surface of the particles are not surrounded by atoms or molecules of their kind on all sides, and hence they possess unbalanced or residual attractive forces. These forces of the adsorbent are responsible for attracting the adsorbate particles on its surface. The extent of adsorption increases with the increase of surface area per unit mass of the adsorbent at a given temperature and pressure. Another important factor featuring adsorption is the heat of adsorption. During adsorption, there is always a decrease in residual forces of the surface, that is, there is decrease in surface energy which appears as heat. Adsorption, therefore, is invariably an exothermic process. In other words, delta H of adsorption is always negative. When a gas is adsorbed, the freedom of movement of its molecules becomes restricted. This amounts to decrease in the entropy of the gas after adsorption, that is, delta S is negative. Adsorption is thus accompanied by decrease in enthalpy as well as decrease in entropy of the system. For a process to be spontaneous, the thermodynamic requirement is that at constant temperature and pressure, delta G must be negative. That is, there is a decrease in Gibbs energy. On the basis of equation, delta G is equal to delta H minus T delta S. Delta G can be negative if delta H has sufficiently high negative values as minus T delta S is positive. Thus, in an adsorption process which is spontaneous, a combination of these two factors makes delta G negative As the adsorption proceeds, delta H becomes less and less negative. Ultimately, delta H becomes equals to T delta S and delta G becomes 0. At this state, equilibrium is attained. Types of adsorption. There are mainly two types of adsorption of gases on solids. If accumulation of gas on the surface of a solid occurs on account of weak van der Waals forces, the adsorption is termed as physical adsorption or physiosorption. When the gas molecules or atoms are held to the solid surface by chemical bonds, the adsorption is termed chemical adsorption or chemiosorption. The chemical bonds may be covalent or ionic in nature. Chemisorption involves a high energy of activation and is therefore often referred to as activated adsorption. Sometimes these two processes occur simultaneously and it is not easy to ascertain the type of adsorption. A physical adsorption at low temperature may pass into chemiosorption as the temperature is increased. For example, dihydrogen is first adsorbed on nickel by van der Waals forces. Molecules of hydrogen then dissociate to form hydrogen atoms which are held on the surfaces by chemiosorption. Some of the following important characteristics of both types of adsorption are described below. Characteristics of physiosorption. First, lack of specificity. A given surface of an adsorbent does not show any preference for a particular gas as the van der Waals forces are universal. Second, nature of adsorbate. The amount of a gas adsorbed by a solid depends on the nature of a gas. In general, easy liquefiable gases, that is, with higher critical temperatures, are readily adsorbed as van der Waals forces are stronger near the critical temperatures. Thus, 1 gram of activated charcoal adsorbed more sulfur dioxide, critical temperature 630 Kelvin, than methane, critical temperature 190 Kelvin, which is still more than 4.5 ml of dihydrogen, critical temperature 33 Kelvin. Third, reversible nature. Physical adsorption of a gas by solid is generally reversible. Thus, solid plus gas equilibrium, gas/solid plus heat. More of a gas is adsorbed when pressure is increased as the volume of the gas decreases, Le Chatelier's principle, and the gas can be removed by decreasing pressure. Since the adsorption process is exothermic, the physical adsorption occurs readily at low temperature and decreases with increasing temperature, Le Chatelier's principle. Fourth, surface area of adsorbent. The extent of adsorption increases with the increase of surface area of adsorbent. Thus, finely divided metals and porous substances having large surface areas are good adsorbents. Fifth, enthalpy of adsorption. No doubt, physical adsorption is an exothermic process, but its enthalpy of adsorption is quite low, 20 to 40 kilojoule mole inverse. This is because the attraction between gas molecules and solid surface is only due to weak van der Waals forces. Characteristics of chemiosorption. First, high specificity. Chemiosorption is highly specific and it will only occur if there is some possibility of chemical bonding between adsorbent and adsorbate. For example, oxygen is adsorbed on metals by virtue of oxide formation and hydrogen is adsorbed by transition metals due to hydride formation. Second, irreversibility. As chemiosorption involves compound formation, it is usually irreversible in nature. Chemiosorption is also an exothermic process, but the process is very slow at low temperatures on account of high energy of activation. With rise of temperature, physiosorption of a gas adsorbed at low temperature may change into chemiosorption at a high temperature. Usually, high pressure is also favorable for chemiosorption. Third, surface area. Like physical adsorption, chemiosorption also increase with increase of surface area of the adsorbent. Fourth, enthalpy of adsorption. Enthalpy of chemiosorption is high, 80 to 240 kilojoule mole inverse, as it involves chemical bond formation. Comparison of physiosorption and chemiosorption. Physiosorption. It arises because of van der Waals forces. Second, it is not specific in nature. Third, it is reversible in nature. Fourth, it depends on the nature of gas. More easily liquefiable gases are adsorbed readily. Fifth, enthalpy of adsorption is low, 20 to 40 kilojoule mole inverse in this case. Chemiosorption. First, it is caused by chemical bond formation. Second, it is highly specific in nature. Third, it is reversible. Fourth, it also depends on the nature of gas. Gases which can react with the adsorbent show chemiosorption. Fifth, enthalpy of adsorption is high, 80 to 240 kilojoule mole inverse in this case. Physiosorption. Sixth, low temperature is favorable for adsorption. It decreases with increase of temperature. Seventh, no appreciable activation energy is needed. Eighth, it depends on the surface area. It increases with an increase of surface area. Ninth, it results into multimolecular layers on adsorbent surface under high pressure. Chemiosorption. Sixth, high temperature is favorable for adsorption. It increases with the increase of temperature. Seventh, high activation energy is sometimes needed. Eighth, it also depends on the surface area. It too increases with an increase of surface area. Ninth, it results into unimolecular layer. Adsorption isotherm. The variation in the amount of a gas adsorbed by the adsorbent with pressure at constant temperature can be expressed by means of a curve termed as adsorption isotherm. Freundlich adsorption isotherm. Freundlich in 1909 gave an empirical relationship between the quantity of gas adsorbed by unit mass of solid adsorbent and pressure at a particular temperature. The relationship can be expressed by the following equation. X upon m is equal to K into P raised to power 1 upon n is greater than 1. Equation number 5.1, where X is the mass of the gas adsorbed on mass m of the adsorbent at pressure P. K and N are constant which depend on the nature of adsorbent and the gas at a particular temperature. The relationship is generally represented in the form of a curve, which is where mass of the gas adsorbed per gram of the adsorbent is plotted against pressure. Figure number 5.1. These curves indicate that at a fixed pressure there is a decrease in physical adsorption with increase in temperature. These curves always seem to approach saturation at high pressure. Taking logarithm of equation 5.1, log x upon m is equal to log k plus 1 upon n into log p. Equation number 5.2. The validity of Freundlich isotherm can be verified by plotting log x upon m on y-axis ordinate and log p on x-axis abscissa. If it comes to be a straight line, the Freundlich isotherm is valid, otherwise not. Figure 5.2. The slope of the straight line gives the value of 1 upon n. The intercept on the y-axis gives the value of log k. Freundlich isotherm explains the behavior of adsorption in an approximate manner, the factor 1 upon n can have values between 0 and 1, probable range 0.1 to 0.5. Thus, equation 5.2 holds good for a limited range of pressure. When 1 upon n is equal to 0, x upon m is equal to constant, the adsorption is independent of pressure. When 1 upon n is equal to 1, x upon m is equal to kp, that is x upon m is directly proportional to p, the adsorption varies directly with pressure. Both the conditions are supported by experimental results. The experimental isotherms always seem to approach saturation at high pressure. This cannot be explained by Freundlich isotherm, thus it fails at high pressure. Adsorption from solution phase. Solids can adsorb solutes from solutions also. When a solution of acetic acid in water is shaken with charcoal, a part of the acid is adsorbed by the charcoal and the concentration of the acid decreases in the solution. Similarly, the litmus solution when shaken with charcoal becomes colorless. The precipitate of MgOH2 attains blue color when precipitated in the presence of magnesium reagent. The color is due to adsorption of magnesium. The following observations have been made in case of adsorption from solution phase. First, the extent of adsorption decreases with an increase in temperature. Second, the extent of adsorption increases with an increase of surface area of the adsorbent. Third, the extent of adsorption depends on the concentration of the solute in the solution. Fourth, the extent of adsorption depends on the nature of the adsorbent and the adsorbate. The precise mechanism of adsorption from solution is not known. Freundlich's equation approximately describes the behavior of adsorption from solution with the difference that instead of pressure, concentration of the solution is taken into account. That is, x upon m is equal to k into c raised to power 1 upon n. C is the equilibrium concentration, that is, when adsorption is complete. On taking logarithm of the above equation, we have log x upon m is equal to log k plus 1 upon n into log c. Plot equation number 5.4. Plotting log x upon m against log c, a straight line is obtained which shows the validity of Freundlich isotherm. This can be tested experimentally by taking solutions of different concentrations of acetic acid. Equal volumes of solutions are added to equal amounts of charcoal in different flasks. The final concentration is determined in each flask after adsorption. The difference in the initial and final concentrations give the value of x. Using the above equation, validity of Freundlich isotherm can be established. Application of adsorption. The phenomenon of adsorption finds a number of applications. Important ones are listed here. First, production of high vacuum. The remaining traces of air can be adsorbed by charcoal from a vessel evacuated by the vacuum pump to give a very high vacuum. Second, gas mask. Gas mask, a device which consists of activated charcoal or mixture of adsorbents, is usually used for breathing in coal mines to adsorb poisonous gases. Third, control of humidity. Silica and aluminium gels are used as adsorbents for removing moisture and controlling humidity. Fourth, removal of coloring matter from solutions. Animal charcoal removes colors of solution by adsorbing colored impurities. Fifth, heterogeneous catalysis. Adsorption of reactants on the solid surface of the catalyst increases the rate of reaction. There are many gaseous reactions of industrial importance involving solid catalysts, manufacture of ammonia using iron as a catalyst, manufacture of H2SO4 by contact process, and use of finely divided nickel in the hydrogenation of oils are excellent examples of heterogeneous catalysis. Sixth, separation of inert gases. Due to the difference in degree of adsorption of gases by charcoal, a mixture of noble gases can be separated by adsorption on coconut charcoal at different temperatures. Seventh, in curing diseases, a number of drugs are used to kill germs by getting adsorbed on them. Eighth, froth flotation process. A low-grade sulfide ore is concentrated by separating it from silica and other earthy matter by this method using pine oil and frothing agent. See Unit 6. Ninth, adsorption indicators. Surfaces of certain precipitates, such as silver halides, have the property of adsorbing some dyes like eosine, fluorescence, etc., and thereby producing a characteristic color at the end point. 10th, chromatographic analysis. Chromatographic analysis based on the phenomenon of adsorption finds a number of applications in analytical and industrial fields. In text questions 5.1, write any two characteristics of chemisorption. 5.2, why does physiosorption decrease with the increase of temperature? 5.3, why are powdered substances more effective adsorbent than their crystalline forms? Catalysis. Potassium chlorate, when heated strongly, decomposes slowly, giving dioxazine. The decomposition occurs in the temperature range of 653 to 873 Kelvin. 2 KClO3 gives 2 KCl plus 3O2. However, when a little of manganese dioxide is added, the decomposition takes place at a considerably lower temperature range, that is 473 to 633 Kelvin, and also at a much accelerated rate. The added manganese dioxide remains unchanged with respect to its mass and composition. In a similar manner, the rates of a number of chemical reactions can be altered by the mere presence of a foreign substance. The systematic study of the effect of various foreign substances on the rates of chemical reactions was first made by Berzelius in 1835. He suggested the term catalyst for such substances which accelerate the rate of a chemical reaction and themselves remain chemically and quantitatively unchanged after the reaction are known as catalysts, and the phenomenon is known as catalysis. You have already studied about catalysts and its functioning in section 4.5. Promoters and poisoners. Promoters are substances that enhance the activity of a catalyst, while poisons decrease the activity of a catalyst. For examples, in Haber's process for manufacture of ammonia, molybdenum acts as a promoter for iron, which is used as a catalyst. N2 gas plus 3H2 gas in presence of Fe solid, molybdenum solid gives 2NH3 gas. Catalysis can be broadly divided into two groups: homogeneous and heterogeneous catalysis. A. Homogeneous catalysis. When the reactants and the catalyst are in the same phase, that is liquid or gas, the process is said to be homogeneous catalysis. The following are some of the examples of homogeneous catalysis. First, oxidation of sulfur dioxide into sulfur trioxide with dioxazine in the presence of oxides of nitrogen as the catalyst in the lead chamber process. 2SO2 gas plus O2 gas in presence of NO gas gives
2SO3 gas. The reactants sulfur dioxide and oxygen and the catalyst nitric oxide are all in the same phase. Second, hydrolysis of methyl acetate is catalyzed by H positive ions furnished by hydrochloric acid. CH3COO CH3 liquid plus H2O liquid in presence of HCl liquid gives CH3COOH aqueous plus CH3OH aqueous. Both the reactants and the catalyst are in the same phase. Third, hydrolysis of sugar is catalyzed by H positive ions furnished by sulfuric acid C12H 22O11 aqueous solution plus H2O liquid in presence of H2SO4 liquid gives C6H12O6 aqueous glucose plus C6H12O6 aqueous fructose. Both are in solution. Both the reactants and the catalyst are in the same phase. B. Heterogeneous catalysis. The catalytic process in which the reactants and the catalyst are in the different phases is known as heterogeneous catalysis. Some of the examples of heterogeneous catalysis are given below. First, oxidation of sulfur dioxide into sulfur trioxide in the presence of platinum. 2SO2 gas in presence of platinum solid gives 2SO3 gas. The reactant is in gaseous state while the catalyst is in the solid state. Second, combination between dinitrogen and dihydrogen to form ammonia in the presence of finely divided iron in Haber's process. N2 gas plus 3H2 gas in presence of iron solid gives 2NH3 gas. The reactants are in gaseous state while the catalyst is in the solid state. Third, oxidation of ammonia into nitric oxide in the presence of platinum goes in Ostwald process. 4NH3 gas plus 5O2 gas in presence of platinum solid gives 4NO gas plus 6H2O gas. The reactants are in the gaseous state while the catalyst is in the solid state. Fourth, hydrogenation of vegetable oils in the presence of finely divided nickel as catalyst. Vegetable oils liquid plus H2 gas in presence of nickel solid gives vegetable ghee solid. One of the reactants is in liquid state and the other in gaseous state while the catalyst is in the solid state. Adsorption theory of heterogeneous catalysis. This theory explains the mechanism of heterogeneous catalysis. The old theory known as adsorption theory of catalysis was that the reactants in gaseous state or in solutions are adsorbed on the surface of solid catalyst. The increase in concentration of the reactants on the surface increases the rate of reaction. Adsorption being an exothermic process, the heat of adsorption is utilized in exchanging the rate of the reaction. The catalytic action can be explained in terms of the intermediate compound formation, the theory of which you have already studied in section 4.5.1. The modern adsorption theory is the combination of intermediate compound formation theory and the old adsorption theory. The catalytic activity is localized on the surface of the catalyst. The mechanism involves 5 steps. First, diffusion of reactants to the surface of the catalyst. Second, adsorption of reactant molecules on the surface of the catalyst. Third, occurrence of chemical reaction on the catalyst surface through formation of intermediate figure 5.3. Fourth, desorption of reaction products from the catalyst surface and thereby making the surface available again for more reaction to occur. Fifth, diffusion of reaction products away from the catalyst surface. The surface of the catalyst, unlike the inner part of the bulk, has free valencies which provide the seat for chemical forces of attraction. When a gas comes in contact with the surface,
With such a surface, its molecules are held up there due to loose chemical combination. If different molecules are adsorbed side by side, they may react with each other, resulting in the formation of new molecules. Thus, formed molecules may evaporate, leaving the surface for the fresh reactant molecules. This theory explains why the catalyst remains unchanged in mass and chemical composition at the end of the reaction and is effective even in small quantities. It, however, does not explain the action of catalytic promoters and catalytic poisons. Figure 5.3 Adsorption of reacting molecules, formation of intermediate and desorption of products. Important features of solid catalyst. For A. Activity. The activity of a catalyst depends upon the strength of a chemisorption to a large extent. The reactants must get adsorbed reasonably strongly on the catalyst to become active. However, they must not get adsorbed so strongly that they are immobilized and other reactants are left with no space on the catalyst surface for adsorption. It has been found that for hydrogenation reaction, the catalytic activity increases from group 5 to group 11 metals, with maximum activity being shown by groups 7 to 9 elements of the periodic table class 12th unit 3. 2H2 gas plus O2 gas in presence of platinum gives 2H2O liquid. B. Selectivity. The selectivity of a catalyst is its ability to direct a reaction to yield a particular product. Selectivity. When under the same reaction conditions, many products are possible. Selectivity of different catalysts for same reactant is different. For example, starting with H2 and CO and using different catalysts, we get different products. First, CO gas plus 3H2 gas in presence of nickel gives CH4 gas plus H2O gas. Second, CO gas plus 2H2 gas in presence of copper or zinc oxide Cr2O3 gives CH3OH gas. Third, CO gas plus H2 gas in presence of copper gives HCHO gas. Thus, it can be inferred that the action of a catalyst is highly selective in nature. As a result, a substance which acts as a catalyst in one reaction may fail to catalyze another reaction. Shape selective catalysis by zeolites. The catalytic reaction that depends upon the pore structure of the catalyst and the size of the reactant and product molecule is called shape selective catalysis. Zeolites are good shape selective catalysts because of their honeycomb-like structures. They are microporous aluminosilicates with three-dimensional network of silicates in which some silicon atoms are replaced by aluminium atoms, giving ALOSI framework. The reactions taking place in zeolites depend upon the size and shape of the reactant and product molecules, as well as upon the pores and cavities of the zeolites. They are found in nature as well as synthesized for catalytic selectivity. Zeolites are being very widely used as catalysts in petrochemical industries for cracking of hydrocarbons and isomerization. An important zeolite catalyst used in petroleum industry is ZSM5. It converts alcohols directly into gasoline petrol by dehydrating them to give a mixture of hydrocarbons. Enzyme catalysis. Enzymes are complex nitrogenous organic compounds which are produced by living plants and animals. They are actually protein molecules of high molecular mass and form colloidal solutions in water. They are very effective catalysts, catalyze numerous reactions, especially those connected with natural processes. Numerous reactions that occur in the bodies of animals and plants to maintain the life process are catalyzed by enzymes. The enzymes are thus termed as biochemical catalysts, and the phenomenon is known as biochemical catalysis. Many enzymes have been obtained in pure crystalline state from living cells. However, the first enzyme was synthesized in the laboratory in 1969. The following are some of the examples of enzyme catalyzed reactions. First, inversion of cane sugar. The invertase enzyme converts cane sugar into glucose and fructose. C12H22O11 aqueous cane sugar plus H2O liquid in presence of invertase gives C6H12O6 aqueous glucose plus C6H12O6 aqueous fructose. Second, conversion of glucose into ethyl alcohol. The zymase enzyme converts glucose into ethyl alcohol and carbon dioxide. C6H12O6 aqueous glucose in presence of zymase gives 2C2H2H5OH aqueous ethyl alcohol plus 2CO2 gas. Third, conversion of starch into maltose. The diastase enzyme converts starch into maltose. 2,6,6H10O5 N aqueous starch plus NH2O liquid in presence of diastase gives C12H22O11 aqueous maltose. Fourth, conversion of maltose into glucose. The maltase enzyme converts maltose into glucose. C12H22O11 aqueous maltose plus H2O liquid maltase gives 2C6H12O6 aqueous glucose. Fifth, decomposition of urea into ammonia and carbon dioxide. The enzyme urease catalyzes this decomposition. NH2CO NH2 aqueous plus H2O liquid urease gives 2NH3 gas plus CO2 gas. Sixth, in stomach, the pepsin enzyme converts proteins into peptides, while in intestine, the pancreatic trypsin converts proteins into amino acids by hydrolysis. Seventh, conversion of milk into curd. It is an enzymatic reaction brought about by lactobacilli enzyme present in curd. Table 5.2 gives the summary of some important enzymatic reactions. Table 5.2 Some enzymatic reactions. Enzyme invertase source yeast enzymatic reaction sucrose to glucose and fructose. Enzyme zymase source yeast enzymatic reaction glucose to ethyl alcohol and carbon dioxide. Enzyme diastase source malt enzymatic reaction starch to maltose. Enzyme maltase source yeast enzymatic reaction maltose to glucose. Enzyme urease source soybean enzymatic reaction urea to ammonia and carbon dioxide. Enzyme pepsin source stomach enzymatic reaction proteins to amino acid. Characteristics of enzyme catalysis. Enzyme catalysis is unique in its efficiency and high degree of specificity. The following characteristics are exhibited by enzyme catalysis. First, most highly efficient. One molecule of an enzyme may transport 1 million molecules of the reactant per minute. Second, highly specific nature.
Each enzyme is specific for a given reaction. That is, for one catalyst cannot catalyze more than one reaction. For example, the enzyme urease catalyzes the hydrolysis of urea only. It does not catalyze hydrolysis of any other amide. Third, highly active under optimum temperature. The rate of an enzyme reaction becomes maximum at a definite temperature called the optimum temperature. On either sides of the optimum temperature, the enzyme activity decreases. Now, optimum range for enzymatic activity is 298 to 310 Kelvin. Human body temperature being 310 Kelvin is suited for enzyme catalyzed reactions. Fourth, highly active under optimum pH. The rate of an enzyme catalyzed reaction is maximum at a particular pH called optimum pH, which is between pH values 5 to 7. Fifth, increasing activity in presence of activators and coenzymes. The enzymatic activity is increased in the presence of certain substances known as coenzymes. It has been observed that when a small non-protein vitamin is present along with an enzyme, the catalytic activity is enhanced considerably. Activators are generally metal ions such as Na+, Mn2+, Cu2+, Cu2+, etc. These metals ions, when weakly bonded to enzyme molecules, increase their catalytic activity. Amylase in presence of sodium chloride, that is Na+ ions, are catalytically very active. Sixth, influence of inhibitors and poisons. Like ordinary catalysts, enzymes are also inhibited or poisoned by the presence of certain substances. The inhibitors or poisons interact with the active functional groups on the enzyme surface and often reduce or completely destroy the catalytic activity of the enzymes. The use of many drugs is related to their action as enzyme inhibitors in the body.
Mechanism of enzyme catalysis. There are number of cavities present on surface of colloidal particles of enzymes. These cavities are of characteristic shape and possesses active groups such as NH2, COOH, SH, OH, etc. These are actually the active centers on the surface of enzyme particles. The molecules of the reactant substrate, which have complementary shape, fit into these cavities just like a key fits into a lock on account of presence of active groups and activated complexes formed, which then decomposes to yield the products. Figure 5.4, Mechanism of enzyme catalyzed reactions. Thus, the enzyme catalyzed reactions may be considered to proceed into two steps. Step 1, binding of enzyme to substrate to form an activated complex. E plus S gives ES star. Step 2, decomposition of the activated complex to form product. ES star gives E plus P. Catalysis in industry. Some of the important technical catalytic processes are listed in table 5.3 to give an idea about the utility of catalyst in industries. Table 5.3, some industrial catalytic processes. First, Haber's process for the manufacture of ammonia. N2 gas plus 3H2 gas gives 2NH3 gas. Catalyst, finely divided iron, molybdenum as promoter, conditions 200 bar pressure and 723 to 773 Kelvin temperature. Nowadays, a mixture of iron oxide, potassium oxide and alumina is used. Second process, Ostwald process for the manufacture of nitric acid. 4NH3 gas plus 5O2 gas gives 4NO gas plus 6H2O gas. 2NO gas plus O2 gas gives 2NO2 gas. 4NO2 gas plus 2H2O liquid plus O2 gas gives 4HNO3 aqueous. Catalyst platinized asbestos. Temperature 573 Kelvin. Third, contact process for the manufacture of sulfuric acid. 2SO2 gas plus O2 gas gives 2SO3 gas. SO3 gas plus H2SO4 aqueous gives H2S2O7 liquid oleum. H2S2O7 liquid plus H2O liquid gives 2H2SO4 aqueous. Platinize asbestos or vanadium pentoxide V2O5, temperature 673 to 723 Kelvin. In-text questions 5.4. In Haber's process, hydrogen is obtained by reacting methane with steam in presence of NiO as catalyst. The process is known as steam reforming. Why is it necessary to remove CO when ammonia is obtained by Haber's process? 5.5. Why is the ester hydrolysis slow in the beginning and becomes faster after some time? 5.6. What is the role of desorption in the process of catalysis? Colloids. We have learned in Unit 2 that solutions are homogeneous systems. We also know that sand in water when stirred gives a suspension which slowly settles down with time. Between the two extremes of suspensions and solutions, we come across a large group of systems called colloidal dispersions or simply colloids. A colloid is a heterogeneous system in which one substance is dispersed phase, as very fine particles in another substance called dispersion medium. The essential difference between a solution and a colloid is that of particle size. While in a solution the constituent particles are ions or small molecules, in a colloid the dispersed phase may consist of particles of a single macromolecule such as protein or synthetic polymer, or an aggregate of many atoms, ions or molecules. Colloidal particles are larger than simple molecules but small enough to remain suspended. Their range of diameters is between 1 to 1000 nanometer, 10⁻⁹ to 10⁻⁶ meter. Colloidal particles have an enormous surface area per unit mass as a result of their small size. Consider a cube with 1 centimeter side. It has a total surface area of 6 centimeter square. If it were divided equally into 10⁻12 cubes, the cubes would be size of large colloidal particles and have a total surface area of 60,000 centimeters square or 6 meters square. This enormous surface area leads to some special properties of colloids to be discussed later in this unit. Classification of colloids. Colloids are classified on the basis of following criteria. First, physical state of dispersed phase and dispersion medium. Second, nature of interaction between dispersed phase and dispersion medium. Third, type of particles of the dispersed phase. Classification based on physical state of dispersed phase and dispersion medium. Depending upon whether the dispersed phase and the dispersion medium are solids, liquids or gases, 8 types of colloidal systems are possible. A gas mixed with another gas forms a homogeneous mixture and hence is not a colloidal system. The examples of the various types of colloids along with their typical names are listed in Table 5.4. Table 5.4 Types of colloidal systems. Dispersed phase, solid. Dispersion medium, solid. Type of colloid, solid sol. Example, some colored glasses and gemstones.
Second, dispersed phase solid, dispersion medium liquid, type of colloid sol, example paints, cell fluids. Third, dispersed phase solid, dispersion medium gas, type of colloid aerosol, example smoke, dust. Fourth, dispersed phase liquid, dispersion medium solid, type of colloid gel, example cheese, butter, jellies. Fifth, dispersed phase liquid, dispersion medium liquid, type of colloid emulsion, example milk, hair cream. Sixth, dispersed phase liquid, dispersion medium gas, type of colloid aerosol, example fog, mist, cloud, insecticide sprays. Seventh, that is dispersed phase gas, dispersion medium solid, type of colloid solid sol, example pumic stone, foam rubber. Eighth, dispersed phase gas, dispersion medium liquid, type of colloid foam, example froth, whipped cream, soap, leather.
Many familiar commercial products and natural objects are colloids. For example, whipped cream is a foam, which is a gas dispersed in a liquid. Firefighting foams used at emergency airplane landings are also colloidal systems. Most biological fluids are aqueous solids dispersed in water. Within a typical cell, proteins and nucleic acids are colloidal sized particles and dispersed in an aqueous solution of ions and small molecules. Out of the various types of colloids given in table 5.4, the most common are sols, solids in liquids, gels, liquids in solids, and emulsions, liquids in liquids. However, in the present unit, we shall take up discussion of the sols and emulsions only. Further, it may be mentioned that if the dispersion medium is water, the sol is called aquasol or hydrosol, and if the dispersion medium is alcohol, it is called as alkosol and so on. Classification based on nature of interaction between dispersed phase and dispersion medium. Depending upon the nature of interaction between dispersed phase and the dispersion medium, colloidal sols are divided into two categories, namely lyophilic solvent attracting and lyophobic solvent repelling. If water is the dispersion medium, the terms used are hydrophilic and hydrophobic. First, lyophilic colloids. The word lyophilic means liquid loving. Colloidal sols directly formed by mixing substances like gum, gelatin, starch, rubber, etc. with a suitable liquid. The dispersion medium are called lyophilic sols. An important characteristic of these sols is that if the dispersion medium is separated from the dispersed phase, say by evaporation, the sol can be reconstituted by simply remixing with the dispersion medium. That is why these sols are also called reversible sols. Furthermore, the sols are quite stable and cannot be easily coagulated as discussed later. Second, lyophobic colloids. The word lyophobic means liquid hating. Substances like metals, their sulfides, etc., when simply mixed with the dispersion medium, do not form the colloidal sol. Their colloidal sols can be prepared only by special method. As discussed later, such sols are called lyophobic sols. These sols are readily precipitated or coagulated on the addition of small amounts of electrolytes by heating or by shaking and hence are not stable. Furthermore, once precipitated, they do not give back the colloidal solution, the colloidal sol, by simple addition of the dispersion medium. Hence, these sols are also called irreversible sols. Lyophobic sols need stabilizing agents for their preservation. Classification based on type of particles of the dispersed phase, multimolecular, macromolecular, and associated colloids. Depending upon the types of particles of the dispersed phase, colloids are classified as multimolecular, macromolecular, and associated colloids. First, multimolecular colloids. On dissolution, a large number of atoms or smaller molecules of a substance aggregate together to form species having size in the colloidal range 1 to 1000 nanometer. The species thus formed are called multimolecular colloids. For example, a gold sol may contain particles of various sizes having many atoms. Sulfur sol consists of particles containing 1000 or more of S8 sulfur molecules. Second, macromolecular colloids. Macromolecules, Unit 15, insoluble solvents form solutions in which the size of the macromolecules may be in the colloidal range. Such systems are called macromolecular colloids. These colloids are quite stable and resemble true solutions in many respects. Examples of naturally occurring macromolecules are starch, cellulose, proteins, and enzymes, and those of man-made macromolecules are polythene, nylon, polystyrene, synthetic rubber, etc. Third, associated colloids, micelles. There are some substances which at low concentrations behave as normal strong electrolytes but at higher concentrations exhibit colloidal behavior due to formation of aggregates. The aggregated particles thus formed are called micelles. These are also known as associated colloids. The formation of micelles takes place only above a particular temperature called Kraft temperature Tk and above a particular concentration called critical micelle concentration CMC. On dilution, these colloids revert back to an individual ions. Surface active agents such as soaps and synthetic detergents belong to this class. For soaps, the CMC is 10 raised to power minus 4 to 10 raised to power minus 3 mole liter inverse. These colloids have both lyophobic and lyophilic parts. Micelles may contain as many as 100 molecules or more. Mechanism of micelle formation. Let us take the example of soap solution. Soap is sodium or potassium salt of a higher fatty acid and may be represented as RCOO negative Na positive. Example, sodium stearate CH3 CH2 16 COO negative Na plus, which is a major component of many bar soaps. When dissolved in water, it dissociates into RCOO negative and Na positive ions. The RCOO negative ions, however, consist of two parts, a long hydrocarbon chain R, also called non-polar tail, which is hydrophobic, water repelling, and a polar group COO negative, also called polar ionic head, which is hydrophilic, water loving. Figure 5.5. Hydrophobic and hydrophilic parts of stearate ion. The RCOO negative ions are therefore present on the surface with their COO negative groups in water, and the hydrocarbon chains are staying away from it and remain at the surface. But at critical micelle concentration, the anions are pulled into the bulk of the solution and aggregate to form a spherical shape with their hydrocarbon chains pointing towards the center of the sphere, with COO negative part remaining outward on the surface of the sphere. An aggregate thus formed is known as ionic micelle. These micelles may contain as many as 100 such ions. Similarly, in case of detergents, example sodium lauryl sulfate CH3 CH2 11 SO4 negative Na plus, the polar group is micelle formation, here also in same as that of soap. Figure 5.6a. Arrangement of stearate ions on the surface of water at low concentrations of soap. B. Arrangement of stearate ions inside the bulk of water ionic micelle at critical micelle concentrations of soap. Cleansing actions of soap. It has been mentioned earlier that a micelle consists of a hydrophobic hydrocarbon like central core. The cleansing action of soap is due to the fact that soap molecules form micelle around the oil droplet in such a way that the hydrophobic part of the stearate ion is in the oil droplet and hydrophilic part projects out of the grease droplet like bristles. Figure 5.7. Since the polar groups can interact with water, the oil droplet surrounded by stearate ion is now pulled in water and removed from dirty surface. Thus, soaps help in emulsification and washing away of oils and fats. The negatively charged sheath around the globules prevents them from coming together and forming aggregates. Figure 5.7. A. Grease on cloth. B. Stearate ions arranging around a grease droplet, and C. Grease droplets surrounded by stearate ions micelle formed. Preparation of colloids. A few important methods for the preparation of colloids are as follows. A. Chemical methods. Colloidal dispersions can be prepared by chemical reactions leading to formation of molecules by double decomposition, oxidation, reduction or hydrolysis. These molecules then aggregate leading to formation of sols. As2O3 plus 3H2S double decomposition gives As2S3 sol plus 3H2O. SO2 plus 2H2S oxidation gives 3S sol plus 2H2O. 2AuCl3 plus 3HCHO plus 3H2O reduction gives 2Au sol plus 3HCOOH plus 6HCl. FeCl3 plus 3H2O hydrolysis gives FeOH3 sol plus 3HCl. B. Electrical disintegration or Braddock's arc method. This process involves dispersion as well as condensation. Colloidal salts of metals such as gold, silver, platinum, etc. can be prepared by this method. In this method, electrical arc is struck between electrodes of the metal immersed in the dispersion medium. Figure 5.8. The intense heat produced vaporizes the metal, which then condenses to form particles of colloidal size. Figure 5.8. Braddock's arc method. C. Peptization. Peptization may be defined as the process of converting a precipitate into colloidal sol by shaking it with dispersion medium in the presence of a small amount of electrolyte. The electrolyte used for this purpose is called peptizing agent. This method is applied generally to convert a freshly prepared precipitate into colloidal sol. During peptization, the precipitate absorbs one of the ions of the electrolyte on its surface. This causes the development of positive or negative charge on precipitates, which ultimately break up into smaller particles of the size of a colloid. Purification of colloidal solutions. Colloidal solutions, when prepared, generally contain excessive amount of electrolytes and some other soluble impurities. While the presence of traces of electrolyte is essential for the stability of the colloid solution, larger quantities coagulate it. It is therefore necessary to reduce the concentration of these soluble impurities to a requisite minimum. The process used for reducing the amount of impurities to a requisite minimum is known as purification of colloidal solution. The purification of colloidal solution is carried out by following methods. First, dialysis. It is a process of removing a dissolved substance from colloidal solution by means of diffusion through a suitable membrane. Since particles, iron or smaller molecules in a true solution can pass through animal membrane, bladder, or parchment paper or cellophane sheet but not the colloidal particles. The membrane can be used for dialysis. The apparatus used for this purpose is called dialyzer. A bag of suitable membrane containing the colloidal solution is suspended in a vessel through which fresh water is continuously flowing. Figure number 5.9. The molecules and ions diffuse through membrane into the outer water and pure colloidal solution is left behind. Figure 5.9. Dialysis. Second, electrodialysis. Ordinarily, the process of dialysis is quite slow. It can be made faster by applying an electric field if the dissolved substance in the impure colloidal solution is only an electrolyte. The process is then named electrodialysis. The colloidal solution is placed in a bag of suitable membrane while pure water is taken outside. Electrodes are fitted in the compartment as shown in figure number 5.10. The ions present in the colloidal solution migrate out to the oppositely charged electrodes. Figure 5.10. Electrodialysis. Third, ultrafiltration. Ultrafiltration is a process of separating the colloidal particles from the solvent and soluble solutes present in the colloidal solution by specially prepared filters, which are permeable to all substances except the colloidal particles. Colloidal particles can pass through ordinary filter paper because the pores are too large. However, the pores of filter paper can be reduced in size by impregnating with collodion solution to stop the flow of colloidal particles. The usual collodion is a 4% solution of nitrocellulose in a mixture of alcohol and ether. An ultrafilter paper may be prepared by soaking the filter paper in a collodion solution, hardening by formaldehyde, and then finally drying it. Thus, by using ultrafilter paper, the colloidal particles are separated from rest of the materials. Ultrafiltration is a slow process. To speed up the process, pressure or suction is applied. The colloidal particles left on the ultrafilter paper are then stirred with fresh dispersion medium solvent to get a pure colloidal solution. Properties of colloidal solutions. Various properties exhibited by the colloidal solutions are described below. First, colligative properties. Colloidal particles being bigger aggregates, the number of particles in a colloidal solution is comparatively small as compared to a true solution. Hence, the values of colligative properties, osmotic pressure, lowering in vapor pressure, depression in freezing point, and elevation in boiling point are of small order as compared to values shown by true solutions at same concentrations. Second, Tyndall effect. If a homogeneous solution placed in dark is observed in the direction of light, it appears clear, and if it is observed from a direction at right angles to the direction of light beam, it appears perfectly dark. Colloidal solutions viewed in the same may also appear reasonably clear or translucent by the transmitted light, but they show a mild to strong opalescence when viewed at right angle to the passage of light, that is, the path of the beam is illuminated by a bluish light. This effect was first observed by Faraday and later studied in detail by Tyndall and is termed as Tyndall effect. The bright cone of the light is called Tyndall cone, figure 5.11. The Tyndall effect is due to the fact that colloidal particles scatter light in all directions in space. This scattering of light illuminates the path of beam in the colloidal dispersion. Figure 5.11 Tyndall effect. Tyndall effect can be observed during the projection of picture in the cinema hall due to scattering of light by dust and smoke particles present there. Tyndall effect is observed only when the following two conditions are satisfied. First, the diameter of the dispersed particle is not much smaller than the wavelength of the light used, and second, the refractive indices of the dispersed phase and the dispersion medium differ greatly in magnitude. Tyndall effect is used to distinguish between a colloidal and a true solution. Zsigmondy in 1903 used Tyndall effect to set up an apparatus known as ultramicroscope. An intense beam of light is focused on the colloidal solution contained in a glass vessel. The focus of the light is then observed with a microscope at right angles to the beam. Individual colloidal particles appear as bright stars against a dark background. Ultramicroscope does not render the actual colloidal particles visible but only observe the light scattered by them. Thus, ultramicroscope does not provide any information about the size and shape of the colloidal particles. Second, color. The color of colloidal solution depends on the wavelength of light scattered by the dispersed particles. The wavelength of light further depends on the size and nature of the particles. The color of colloidal solution also changes with the manner in which the observer receives the light. For example, a mixture of milk and water appears blue when viewed by the reflected light and red when viewed by the transmitted light. Finest gold sol is red in color. As the size of particle increases, it appears purple, then blue, and finally golden. Fourth, Brownian movement. When colloidal solutions are viewed under a powerful ultramicroscope, the colloidal particles appear to be in a state of continuous zigzag motion all over the field of view. This motion was first observed by the British botanist Robert Brown and is known as Brownian movement, figure 5.12. This motion is independent of the nature of the colloid but depends on the size of the particles and viscosity of the solution. Smaller the size and lesser the viscosity, faster is the motion. Figure 5.12, Brownian motion. The Brownian movement has been explained to be due to the unbalanced bombardment of the particles by the molecules of the dispersion medium. The Brownian movement has a steering effect which does not permit the particles to settle and thus is responsible for the stability of sols. Fifth, charge on colloidal particles. Colloidal particles always carry an electric charge. The nature of this charge is the same on all particles in a given colloidal solution and may be either positive or negative. A list of some common sols with the nature of charge on their particles is given below. Positively charged sols. Hydrated metallic oxides, example Al2O3.XH2O, CrO3.XH2O and Fe2O3.XH2O, etc. Basic diesters, example methylene blue sol, hemoglobin blood oxides, example TiO2 solution. Negatively charged sols, metal, example copper, silver, gold sols. Metallic sulfides, example As2S3, Sp2S3, CdS sols. Acid dyestuffs, example leucine, Congo red sols. Sols of starch, gum, gelatin, clay, charcoal, etc. The charge on the sol particles is due to one of more reasons, viz. Due to electron capture by the sol particles during electrodispersion of metals, due to preferential adsorption of ions from solution, and or
due to formulation of electrical double layer. Preferential adsorption of ions is the most accepted reason. The soul particles acquire positive or negative charge by preferential adsorption of positive or negative ions. When two or more ions are present in the dispersion medium, preferential adsorption of the ion common to the colloidal particle usually take place. This can be explained by taking the following examples. A. When silver nitrate solution is added to potassium iodide solution, the precipitated silver iodide adsorbs iodide ions from the dispersion medium and negatively charged colloidal salt results. However, when Ki solution is added to AgNO3 solution, positively charged salt results due to adsorption of Ag plus ions from dispersion medium. Agi/I negative, negatively charged, Agi/Ag positive, positively charged. B. If FeCl3 is added to excess of hot water, a positively charged salt of hydrated ferric oxide is formed due to adsorption of Fe3 plus ions. However, when ferric chloride is added to NaOH, a negatively charged salt is obtained with adsorption of OH negative ions. Fe2O3.xH2/Fe3 plus positively charged, Fe2O3.xH2/OH negative, negatively charged. Having acquired a positive or a negative charge by selective adsorption on the surface of a colloidal particle, as stated above, this layer attracts counter ions from medium, forming a second layer as shown below. Agi/I negative K positive and Agi/Ag positive I negative. The combination of the two layers of opposite charges around the colloidal particles is called Helmholtz electrical double layer. According to modern views, the first layer of ions is firmly held and is termed fixed layer, while the second layer is mobile, which is termed diffused layer. Since separation of charge is a seat of potential, the charges of opposite signs on the fixed and diffused parts of the double layer results in a difference in potential between these layers. This potential difference between the fixed layer and the diffused layer of opposite charges is called the electrokinetic potential or zeta potential. The presence of equal and similar charges on colloidal particles is largely responsible in providing stability to the colloidal solution, because the repulsive forces between charged particles having same charge prevent them from coalescing or aggregating when they come closer to one another. Sixth, electrophoresis. The existence of charge on colloidal particles is confirmed by electrophoresis experiment. When electric potential is applied across two platinum electrodes, dipping in a colloidal solution, the colloidal particles move towards one or the other electrode. The movement of colloidal particles under an applied electric potential is called electrophoresis. Positively charged particles move toward the cathode, while negatively charged particles move towards the anode. This can be demonstrated by following experimental setup. Figure 5.13. Figure 5.13 electrophoresis. When electrophoresis, that is movement of particle, is prevented by some suitable means, it is observed that the dispersion medium begins to move in an electric field. This phenomenon is termed electroosmosis. Seventh, coagulation or precipitation. The stability of the lyophobic salts is due to the presence of charge on colloidal particles. If somehow the charge is removed, the particles will come nearer to each other to form aggregates or coagulate and settle down under the force of gravity. The process of settling of colloidal particles is called coagulation or precipitation of the salt. The coagulation of the lyophobic soils can be carried out in the following ways. First, by electrophoresis, the colloidal particles move towards oppositively charged electrodes, get discharged and precipitated. Second, by mixing two oppositely charged soils. Oppositely charged soils, when mixed in almost equal proportions, neutralize their charges and get partially or completely precipitated. Mixing of hydrated ferric oxide positive soul and arsenious sulfide negative soul, bring them in the precipitated forms. This type of coagulation is called mutual coagulation. Third, by boiling. When a soul is boiled, the adsorbed layer is disturbed due to increased collisions with the molecules of dispersion medium. This reduces the charge on the particles and ultimately leads to settling down in the form of precipitate. Fourth, the persistent dialysis. On prolonged dialysis, traces of the electrolyte present in the soul are removed almost completely and the colloids become unstable and ultimately coagulate. Fifth, by addition of electrolytes. When excess of an electrolyte is added, the colloidal particles are precipitated. The reason is that colloids interact with ions carrying charge opposite to that present on themselves. This causes neutralization leading to their coagulation. The ion responsible for neutralization of charge on the particles is called the coagulation ion. A negative ion causes the precipitation of positively charged soul and vice versa. It has been observed that generally the greater the valency of the flocculating ion added, the greater is its power to cause precipitation. This is known as Hardy-Scott's rule. In the coagulation of a negative soul, the flocculating power is in the order Al3 plus greater than Ba2 plus greater than Na plus. Similarly, in the coagulation of a positive soul, the flocculating power is in the order FeCN6 whole power 4 negative greater than PO4 3 negative greater than SO4 2 negative greater than Cl negative. The minimum concentration of an electrolyte in millimoles per liter required to cause precipitation of a soul in 2 hours is called coagulating value. The smaller the quantity needed, the higher will be coagulating power of an ion. Coagulation of lyophilic soils. There are two factors which are responsible for the stability of lyophilic soils. These factors are the charge and solvation of the colloidal particles. When these two factors are removed, a lyophilic soil can be coagulated. This is done first by adding an electrolyte and second by adding a suitable solvent. When solvents such as alcohol and acetone are added to hydrophilic soils, the dehydration of dispersed phase occurs. Under this condition, a small quantity of electrolyte can bring out coagulation. Protection of colloids. Lyophilic soils are more stable than lyophobic soils. This is due to the fact that lyophilic colloids are extensively solvated, that is, colloidal particles are covered by a sheet of the liquid in which they are dispersed. Lyophilic colloids have a unique property of protecting lyophobic colloids. When a lyophilic soul is added to the lyophobic soul, the lyophilic particles form a layer around lyophobic particles and thus protect the latter from electrolytes. Lyophilic colloids used for this purpose are called protective colloids. Emulsions. These are liquid-liquid colloidal systems, that is, the dispersion of finely divided droplets in another liquid. If a mixture of two immiscible or partially miscible liquid is shaken, a coarse dispersion of one liquid in the other is obtained, which is called emulsion. Generally, one of the two liquids is water. There are two types of emulsion. First, oil dispersed in water O/W type, and second, water dispersed in oil W/O type. In the first system, water acts as dispersion medium. Example of these emulsions are milk and vanishing cream. In milk, Liquid fat is dispersed in water. In the second system, oil acts as dispersion medium. Common example of this type are butter and cream. Figure 5.14 Types of emulsions. Emulsions of oil in water are unstable and sometimes they separate into layers on standing. For stabilization of an emulsion, a third component called emulsifying agent is usually added. The emulsifying agent forms an interfacial film between suspended particles and the medium. The principal emulsifying agents for O/W emulsions are proteins, gums, natural and synthetic soaps, etc. And for W/O, heavy metal salts of fatty acids, long chain alcohols, lamp black, etc. Emulsions can be diluted with any amount of the dispersion medium. On the other hand, the dispersed liquid, when mixed, forms a separate layer. The droplets in emulsions are often negatively charged and can be precipitated by electrolytes. They also show Brownian movement and Tyndall effect. Emulsions can be broken into constituent liquids by heating, freezing, and centrifuging, etc. Colloids around us. Most of the substances we across in our daily life are colloids. The meals we eat, the clothes we wear, the wooden furniture we use, the houses we live in, the newspapers we read, and are largely composed of colloids. Following are the interesting and noteworthy example of colloids. First, blue color of the sky. Dust particle along the with water suspended in air scatter blue light which reaches our eyes and sky looks blue to us. Second, fog, mist and rain. When a large mass of air containing dust particles is cooled below its dew point, the moisture from the air condenses on the surface of these particles, forming fine droplets. These droplets, being colloidal in nature, continue to float in air in the form of mist or fog. Clouds are aerosols having small droplets of water suspended in air. On account of condensation in the upper atmosphere, the colloidal droplets of water grow bigger and bigger in size till they come down in the form of rain. Sometimes the rainfall occurs when two oppositely charged clouds meet. It is possible to cause artificial rain by throwing electrified sand or spraying a soul carrying charge opposite to the one on clouds from an aeroplane. Third, food articles, milk, butter, halwa, ice cream, fruit juices, etc. are all colloids in one form or the other. Fourth, blood. It is a colloidal solution of an albuminoid substance. The styptic action of alum and ferric chloride solution is due to coagulation of blood forming a clot which stops further bleeding. Fifth, soils. Fertile soils are colloidal in nature, in which humus acts as a protective colloid. On account of colloidal nature, soils absorb moisture and nourishing materials. Sixth, formation of delta. River water is a colloidal solution of clay. Sea water contains a number of electrolytes. When river water meets the sea water, the electrolytes present in sea water coagulate the colloidal solution of clay, resulting in its deposition with the formation of delta. Application of colloids. Colloids are widely used in the industry. Following are some examples. First, electrical precipitation of smoke. Smoke is a colloidal solution of solid particles such as carbon, arsenic compounds, dust, etc. in air. The smoke, before it comes out from chimney, is led through a chamber containing plates having a charge opposite to that carried by smoke particles. The particles, on coming in contact with these plates, lose their charge and get precipitated. The particles thus settle down on the floor of the chamber. The precipitator is called Cottrell precipitator, figure 5.15. Figure 5.15 Cottrell smoke precipitator. Second, purification of drinking water. The water obtained from natural sources often contains suspended impurities. Alum is added to water to coagulate the suspended impurities and make water fit for the drinking purposes. Third, medicines. Most of the medicines are colloidal in nature. For example, Argyrol is a silver salt used as an eye lotion. Colloidal antimony is used in curing Kala-Azar. Colloidal gold is used for intramuscular injection. Milk of magnesia and emulsion is used for stomach disorders. Colloidal medicines are more effective because they have large surface area and are therefore easily assimilated. Fourth, tanning. Animal hides are colloidal in nature. When a hide which has positively charged particles is soaked in tannin which contains negatively charged colloidal particles, mutual coagulation takes place. This results in hardening of leather. This process is termed as tanning. Chromium salts are also used in place of tannin. Fifth, cleansing action of soaps and detergents. This has already been described in section 5.4.3. Sixth, photographic plates and films. Photographic plates or films are prepared by coating an emulsion of the light-sensitive silver bromide in gelatin over glass plates or celluloid films. Seventh, rubber industry. Latex is colloidal solution of rubber particles which are negatively charged. Rubber is so obtained by coagulation of latex. Eighth, industrial products, paints, inks, synthetic plastics, rubber, graphite, lubricants, cement, etc. all are colloidal solutions. In text question 5.7, what modification can suggest in the Hardy-Scott's law? 5.8 Why is it essential to wash the precipitate with water before estimating it quantitatively? Summary. Adsorption is a phenomenon of attracting and retaining the molecules of a substance on the surface of a solid, resulting into a higher concentration on the surface than in the bulk. The substance adsorbed is known as adsorbate, and the substance on which adsorption takes place is called adsorbent. In physiosorption, adsorbate is held to the adsorbent by weak van der Waals forces, and in chemisorption, adsorbate is held to the adsorbent by strong chemical bond. Almost all solids adsorb gases. The extent of adsorption of a gas on a solid depends upon nature of a gas, nature of solid, surface area of solid, pressure of a gas and temperature of gas. The relationship between the extent of adsorption x upon m and pressure of a gas at constant temperature is known as adsorption isotherm. A catalyst is a substance which enhances the rate of a chemical reaction without itself getting used up in the reaction. The phenomenon using catalyst is known as catalysis. In homogeneous catalysis, the catalyst is in the same phase as are the reactants, and in heterogeneous catalysis, the catalyst is in the different phase from that of the reactants. Colloidal solutions are intermediate between true solution and suspensions. The size of the colloidal particles range from 1 to 1000 nanometer. A colloidal system consists of two phases, the dispersed phase and the dispersion medium. Colloidal systems are classified in three ways depending on first, physical state of dispersed phase and dispersion medium. Second, nature of interaction between the dispersed phase and dispersion medium. And third, nature of particles of dispersed phase. The colloidal systems show interesting optical, mechanical and electrical properties. The process of changing the colloidal particles in a sol in the insoluble precipitate by addition of some suitable electrolytes is known as coagulation. Emulsions are colloidal systems in which both dispersed phase and dispersion mediums are liquids. These can be of first oil in water type and second water in oil type. The process of making emulsion is known as emulsification. To stabilize an emulsion, an emulsifying agent or emulsifier is added. Soaps and detergents are most frequently used as emulsifiers. Colloids find several applications in industry as well as in daily life.